Hey everyone. We are going to be talking about data visualization today. One of the what we're going to start with actually is just talking a little bit about univariate data visualization, and then we're going to move into multivariate visualization, specifically as it relates to regression and addressing some of the issues with assumptions that we have within regression. We're going to use a data set that I put up for this video, and we're going to be using this actually for the next video and for class as well. But just looking at this data set, we have protective behavioral strategies, a total score, and then we have three different types of protective behavioral strategies: harm, stopping, limiting, and manner of drinking. We have urgency, conscientiousness, sensation seeking, and then consumption problems, and then total audit score. So this is some basic types of data that I typically wind up working with. And so let's start by today what we're going to look at. Sorry, get out of here. Today what we're going to be looking at is the relationship between protective behavioral strategies and conscientiousness. There's research suggesting that protective behavioral strategies work um, through conscientiousness to promote, to reduce alcohol-related problems. So that's what we're going to look at today. Uh, what we're going to be doing primarily is just looking at our data to make sure that it is not problematic. So we're going to start by looking at basic univariate stuff. So we're going to go analyze descriptives, explore, and let's look at PBS tote, and let's look at, come on, conscientiousness. A friend over there is working on something. Let's look at our statistics. We don't need M estimators, but we want to see outliers, percentiles, or descriptives. Let's look at plots. We want to look both at stem and leaf and histogram plots, and we're going to look at some normality plots with some tests of normality. And as far as options, yeah, we'll exclude cases list-wise. And just for the heck of it, let's do this also. Let's look at consumption, and then let's look at problems, because I want us to have a couple of good variables to look at and a couple of really bad variables to look at. And consumption and problems often wind up being a very bad variable for us. All right, and let's pull this down. Come on, you. There we go. Okay, so we have PBS total, conscientiousness, consumption, and problems. Let's start by just talking about the basic descriptives for all of these things. So for PBS, we have an average score of 3.2 and a standard error of 0.03. Here is our confidence intervals, median, variance, standard deviation, minimum and maximum, a range of 5 values. Here's our skew statistic. And here's our kurtosis statistic. These are interesting things to note because we want to have roughly normally distributed data. And so a negative skew indicates that we have skew towards the right-hand side. A positive skew will indicate skew towards the left-hand side. And this is a standard error, which means you can divide this by this, and you will get a z statistic, and that will tell you if you have significant skew. Almost always you will have significant skew. The same applies here to kurtosis, though it doesn't look like you will have significant kurtosis. Rule of thumb, if your skew is greater than plus or minus the absolute value of 2, then it becomes problematic. In kurtosis, if it's greater than the absolute value of 4, then it becomes problematic. And in a few weeks, we will talk about how to deal with that. I might show you a little bit today of how to deal with some of that. Recall that we are not too concerned with the distribution of our variables. More so, we are concerned with the distribution of our residuals, and that's what we'll be focusing on today. Consumption, we have the same variables. We have skew. Again, it's negative skew. Oh, I'm sorry, this is conscientiousness, not consumption. And for consumption, we actually have positive skew. That means that we're going to have skew on our left-hand side, and we'll see that in a second when we take a look at this. And of course, this is going to be significant. It always is with alcohol use. But it's under 2, we're fine there. This is under 4, we're fine there. Problems is the one that always causes us issues. And if you look here, you'll see that our skew is 4 and our kurtosis is 23. That means it is highly kurtotic, a strong peak of our data at some point, and for problems, that peak always occurs right around 0. You can see our minimum is 0 problems, and so we know what we're going to find when we scroll down and look at this. Percentiles, we don't need to worry about that. Here is a list of our extreme values and the case number for those extreme values. We have our high values. Obviously, 5 is the top number for PBS, 4 is the top number for conscientiousness, 0 here. So we kind of expect these. There's more than 5 fives. It picks out the first 5 values that we have. Notice we've got a data set with like 1,500 people. So if we scroll down here, we have for problems, 5 being the most problems, and then of course 0 being the least. And then if we continue kind of working our way down, we get to tests of normality. This is with ANOVA, you get a Levene's test, right, or something along those lines, or regression. These are not Levene's tests. This is just a straight test of normality of our data, and you can see every one of these suggests that our data is not normally distributed. However, if we look at it, it actually doesn't look that bad, right? So we have a rough normal distribution with some peaks here and here and here and here, and then this guy over here. And this is because we have a bunch of people who don't drink at all, and so they report no protective behavioral strategy use. That's the histogram. Of course, our stem and leaf plots look very similar. The nice thing about stem and leaf plots is they kind of break this up and tell you exactly how many are in here. If we continue down, we have a normal QQ plot. These are quantile plots. This actually doesn't look too bad. For QQ plots, you always want your variable to kind of fit right on this line. Tails often get deviated from that line. And this is a detrended QQ plot. This is actually basically the same information that you get up here, but it tells you how far these things are from this basic line, right? And so you get these values, notice, are much different than the values along here. Correction. So, then we get to our box plots. This box plot looks pretty good. You can see, obviously, there is skew. We already knew that there was skew. One of the nice things about box plots in SPSS is they will give you outliers if there are outliers, and there aren't in this one. No extreme outliers anyway, so that doesn't look bad. Here is our conscientiousness variable. That also does not look too bad. Looks fairly normally distributed. And remember that our Q or our skew and kurtosis looked pretty decent here. It does look a little kurtotic, but not bad. If you want, you can double click on that and you can fit a normal distribution to it. You can also try other curves if you want, but it actually looks like a normal distribution fits that pretty nicely. Continue scrolling down here. There's our QQ plot. Again, looks good. We are starting to get some outliers associated with this variable, though. And was that? Yep, that's conscientiousness. All right, consumption. So we can see that consumption has a positive skew, right, as we had said before. And if we fit a distribution to this, it doesn't look like a great normal distribution. And in fact, oftentimes what we see with alcohol use data is a sort of a Poisson or a negative binomial type of distribution, and that looks like what we've actually got here, right? So we can throw that on there. We can kind of assume that that's Poisson. You don't need to worry about that right now. If you wind up taking ARM 3 with me, we'll talk a little bit more about Poisson. Here, our QQ plot doesn't look bad, but you can see it's not just the tail anymore, right? This is actually at about the midpoint that we start deviating away. So there's some problems with our consumption variable. Lots of outliers or potential outliers. And just because something is listed in here as a potential outlier, that doesn't mean that it's bad, and it doesn't mean that it needs to be thrown out. We're going to do some regression models here in a second, and we'll identify whether or not there are serious problems with any of these observations. This is problematic. This is our problems variable. You can see it is strongly skewed, strongly kurtotic. It does not fit any of our typical, it certainly doesn't fit a normal distribution if you try and plug a normal distribution on there. In fact, it seems to fit far better an exponential distribution, right? And there are ways to handle exponential distributions. And we will talk about that in a few weeks. QQ plot looks terrible. But again, remember that these are less important right now. What's most important is the distribution of residuals and, of course, all kinds of outliers. And note that these outliers are starred. Those stars mean that they are several standard deviations. I believe they start starring them at 3 standard deviations away from, not from the mean, but from this 95% error bars. So, all right, you know what? Let's hop back over here and let's talk about something else. So we've looked at our data. We know that we have some variables that look pretty decent, and we have some variables that don't look good at all. For right now, we are not going to worry about the heavily skewed data. We're only going to do regressions with our regular data, or with our non-skewed data, and we are going to look at kind of our basic assumptions that underlie linear regression models. Now, one of our assumptions is that there is no measurement error in our independent variables, that they are perfectly reliable. We know that in practice that is almost never true, and this winds up being an issue that we have that we have to either note if we're using regression in our analysis. We'll have to note this as a limitation that probably is not measured perfectly. And in fact, nothing ever is. But let's do this. Let's go analyze, regress, and we're going to do an actual regression model. We're going to predict conscientiousness from our 3 different types of protective behavioral strategies. In this instance, we're not going to add anything to block 2 or block 3. We're going to talk about that next time, but we're not going to do it this time. All right, so we're going to want our regression coefficients. Let's get some residuals here. Model fit, R-squared, descriptive statistics, part and partial correlations, and collinearity diagnostics. This is something that we haven't talked about before, and we're going to talk about here today. Plots. We want to get some plots, and we're going to get plots of our residuals by our predicted. Continue. Let's save our unstandardized and standardized residuals and our unstandardized and standardized predicted values. We don't need to include the covariance matrix. In a few weeks, we will talk about examining multivariate normality using Mahalanobis distance, Cook's distance, leverage values, as well as influence statistics over here, but we're not going to do those just yet. We're just talking about having a look at what these things kind of look like. So we hit go, we run our regression model, And here we go. We have our basic descriptive statistics right here, mean, standard deviation, and n for all of our stuff. You know what? Actually, let's do something. Let's flip over here. Let's go data, select cases, and let's only look at people who are drinking. So we're going to only look at people who report that they drink, and 5 means that their data is that they answered 5 if they didn't want to respond. So let's grab those people. Hello, data. Where'd you go? There we are. All right, I'm going to delete these things that we just had, and let's rerun our regression model that we just ran. So analyze, regression, linear, there we go, everything should be checked. Means will change a little bit because now notice we have 1,200 people. It removed a bunch of people that don't drink. And as we scroll down here, we see our model R is 0.16, R squared 0.026. That is not a great R squared. But here we go. Here are our regression coefficients. And you can see that every one of these significantly predicts conscientiousness. Interestingly, from a theory perspective that you probably don't care or need to care about, stopping limiting drinking seems to be inversely associated with conscientiousness. And then if we look over here, let's talk, we've already done this, we understand what these things mean. Let's talk about what these mean, because these are the statistics that tell us if one of our predictors is problematic within our model. Tolerance winds up being a proportion, and it's not a proportion that has any true meaning, but a proportion of variance that winds up being uniquely associated with each one of these. If this is less than 0.1, then that is problematic. VIF stands for variance inflation factor, and it's really just 1 divided by tolerance. If this is greater than 10, then your variance for any one of these variables is being inflated, and you've got some sort of misspecification in your model. Perhaps what it typically means is that you have 1 or 2 variables that are very, very highly correlated, and so these are ways that you can detect some sort of suppression effect or something along those lines. Okay, anyway, our VIF looks good. This is a little bit high, but other than that, not too bad. Let's keep going down. Here are our variance proportions. None of these look that great, but you can see that there are kind of multiple dimensions of each one of these, and PBS-MD seems to be kind of roughly the most important factor, though its proportion of variance is spread a little bit. The proportion of variance for PBS harm is all the way down here on the 4th dimension. Don't worry about that for right now. We will get into that a little bit later. Residuals. We're not going to worry about this table because we're going to look at the values of residuals. Here is a histogram of our dependent variable and the frequency of residuals across our dependent variable, and that looks pretty good. The next thing that we get is a PP plot, and this is the expected cumulative probability across our regression model by our observed cumulative probability. It can range from 0 to 1. Ideally, it maps right along this line from 0 to 1. And notice that the tails wind up hugging that line closely here. This is good. That indicates good fit, and it's different than what we're going to see with a QQ plot. All right, here's the first thing that's really important to us. This is how we start looking at homogeneity of variance. What we ideally want to see is most of these residuals, this is our residuals, our standardized residuals plotted against our standardized predicted values. we want our residuals to maximize 0. So most of them should be clustered right around 0. And then they should spread out in either direction. This looks a little problematic right here and a little problematic right here. But overall, this doesn't look too bad. Let's double click on this because we can do something. When we fit a line to this, a regression line, come on you, that regression line should go straight across. And so let's go elements, fit line at total, and there it is. Regression line goes straight across. Now, one of the things that we might be interested in, or that we definitely are interested in, is whether or not there is homogeneity of variance. And if there's perfect homogeneity of variance, that means that the variance does not differ at any point on this line, then this line will remain perfectly straight all the way across if we fit a Lowe's line to it. So let's fit a Lowe's line and let's see if this line stays perfectly straight. Not perfectly straight, but you know what? That is not too bad, right? That is a decent line going through there. It could be a little bit better. What if we do this? Same. No, it looks good. Okay, so we're going to close out of this. If you hit close, it'll drop that line in there. It'll stay in there for you. And there it is. Doesn't look bad. And this, I think we can roughly conclude that we have homogeneity of variance across there. Now remember when we talked about some of the other variables or other graphs that we can look at when it comes to regression models? Let's do that real quick. Let's go graphs, chart builder, and let's look at our standardized residuals. And let's not do PBS. Let's look at conscientiousness. Now recall, if we look at our residuals and our outcome variable, what sort of fit should we have there? If you said a perfect correlation or something dang near perfect, you're right. And that is what we should see. And that is roughly what we have here. Basically a perfect correlation between standardized residuals and our actual outcome variable. We can also look then at standardized residuals and our predictor variable. And so we have multiple predictor variables here, but let's just grab one, PBS harm. And if you recall, these should be 0, right? There should be no relationship. And that looks an awful lot like no relationship. We can go ahead and we can come in here, elements, fit line at total. And yeah, that is no relationship. You can add a Lowe's line, should stay extremely flat here. Yeah, that's not bad. So I think that we can rightly conclude that we have homogeneity of variance here. Now in ANOVA, you get a test, a Levene's test or something like that. In regression, you can roughly calculate a Levene's test if you want by breaking your dependent variables up by groups or something along those lines. We're not going to do that here. We're just going to go with what we've got. So anyway, these are the kind of basic things that we are looking for when we are trying to fit a regression model. Just to go through and look at the data, let's take one more example because everything that we've looked at here has looked pretty nice. Let's try this. Analyze, regression. Oh, you know what? First, let's flip over here. Let's get rid of these. And let's go analyze, regression, linear. And let's take conscientiousness out and let's put in audit problems. And let's even use something that we know predicts problems really well, which is consumption. We're going to use the same statistics. We want all the same statistics, same plots. Don't worry about options. Same saves, standardized, unstandardized. Continue. Let's go. So we have our same basic statistics here. You can see that alcohol is a very strong predictor. Alcohol drinks is a very strong predictor of alcohol problems. Note though, it's not a perfect predictor. How much you drink does not perfectly predict how many problems you have. Not that that really matters, but right here, collinearity and variance, 1 and 1, that is perfect. Do you know why it's perfect? It's because we only have one predictor in the model. It can't have influence from other variables. It can't overlap with other variables. So these are very good, or they're not good or bad, I guess. They're just one. I mean, if we put another variable in the model, then we could see if they were really problematic. In fact, you know what? Let's do something really well. We'll come back to that. All right. So we scroll down. There is our regression, standardized residuals. It looks really bad, right? PP plot looks terrible. That stuff is not falling on that line. Remember last time it fell almost perfectly on this line. We have some serious issues here. And here is our scatter plot. Let's do what we did before. Elements, fit line at total. There's our line, and let's change this to a Lowe's line. Apply. That looks pretty bad, right? No longer is it a nice kind of straight line, or even a straight line with just a little bit of curve. We can see that there is some serious issues here. We do not have good homogeneity of variance, or at least that's what I would conclude from this. Let's look at our graphs here quick. Chart builder. So we have standardized residuals. Our outcome was problems. Let's look at this. Remember, this should be a perfect predictor, right? Should be very tight. Not good at all. That looks terrible. Analyze, oops, graphs, chart builder, and consumption by standardized residuals. This looks very problematic because it looks kind of uniform here, right? In fact, it doesn't look all that different from this. We do not have good homogeneity of variance here. This can be for a number of reasons. One of those reasons is oftentimes that we do not have a linear relationship. We are assuming a linear relationship when we don't really have one. We're going to talk about in a few weeks how to test for nonlinear relationships, and indeed what you often find with alcohol. Let's just do it real quick. Let's go transform, compute. Let's go alk2 equals, we're going to go consumption times consumption. And if we go analyze, I haven't run this, so I don't know if this is going to come out, but I think it will come out. Alk2. See what happens here. R squared went up drastically from what it was before. All I did was square this. Squaring it means I'm going to assume that there is a quadratic effect, a nonlinear effect. And look at there, we have a very strong quadratic effect. And this negative means that it actually does a deal like this. We come down. Let's look at our graphs. Of course, that looks terrible. You know what? That looks better than it did before, doesn't it? That still doesn't look the greatest. let's do one more thing. Transform, compute. Let's go times con alc3. This is assuming some sort of a cubic effect. And again, don't get too worried about this. Don't get too bent up around the axle because we are going to go through nonlinear effects in a couple of weeks. Let's just see if this fixes some of the problems that we were seeing. Doesn't actually change r squared that much. I'm gonna guess that there is, oh yeah, so it winds up being somewhat problematic here, right? Look at this. So this right here, way more than 10, way less than 0.1, would lead us to conclude that there is no cubic effect, and we would not worry about cubic. This is also a little bit scary if we scroll up here. We're sitting right at 10. Now, granted, these two variables are highly interrelated. I would be okay with this, given that it's just that these two variables are squared, right? This variable, this consumption, is just, or this alk2 is just consumption squared. You would expect there to be a lot of overlap between the two. There is no cubic function, though. That looks like garbage again, and that doesn't look very good either. Anyway, that is one of the issues. Perhaps it's nonlinear. Another is that we have non-independence of residuals, or of observations, I mean. And in this case, we could have people who have been in there multiple times, who have completed this exactly the same way, something along those lines. There could also be, there can be a number of different reasons, and we'll talk about those in class for that occurring. Some of the remedies for this, we can, as I did, look at the form of the relationship, and it seems that in this instance at least, we have a linear or a nonlinear relationship between alcohol use and problems. One of the other issues is that we might be missing other important or relevant independent variables. And so we should have a look at ways that we can identify variables that might be missing, or at least control for some other aspects. One final note is we can do something called data transformations. We can do these both on the independent variable as well as the dependent variable, although I'm not a huge fan of doing it on dependent variables. But if it helps to bring our residuals back into normal distribution, then it can be an important tool. We're going to talk about transformations in a couple of weeks, so I'm not going to go into it here. Anyway, this was basic data visualization for initial regression analysis and trying to troubleshoot some problems that we might have. I will see you all in class.